Okay, carrying on. Defining a few things for deformation of solids. Elastic deformation. Essentially, when you look at the definition, I would search the internet for this one, but if you have something that goes up in a straight line like that on your stress and strain graph, we could say it's elastic. That's because as it stretches, it's going to head up and then it's going to come back down the same path and it's going to not change the original length. So you could define it as extension where, or deformation, sorry, where the original length of the sample will remain unchanged, or once the thing has been deformed it will return back to its original length. Plastic deformation, however, is where you can get a curve at the end of your graph, any sort of shape. Okay, what we're saying there is that as you go up there, and then the thing is going to return and end up being at a different original length. Ultimate tensile stress, UTS, okay, that's where it breaks. Okay, it goes into little pieces. Now when you're looking at this sort of stuff, it's important to look at the structure of how the solids are made up. Some interesting ones. Crystalline solids, okay, so these ones show a regular pattern, they're quite strong. Minerals and so on, you imagine salt, NaCl. Polycrystalline solids are just usually all your metals, they're made up of small crystals. So you can look here, this is aluminium under a microscope, there's a crystal, and then there's another crystal beside it. Okay, so it's just made up of many crystals. Amorphous solids, essentially just dried and formed into any sort of haphazard pattern. There's good bonding there, but there's no routine structure. Okay, so usually you wouldn't make it, it wouldn't end up being a square sort of block if you formed it. Polymers, you know, you got your nylons and so on. Okay, so it's a repeating chain. Okay, crystalline polymers, rigid. Amorphous polymers are flexible and so on. Okay, and that can lead to polymeric behavior, which we'll look at soon. So when you're looking at some of these objects, ductile material, okay, a ductile material is one where it expands elastically and then heads into a plastic deformation section. Okay, so an example of this would be something like copper. Okay, that is a ductile material, because you could grab a tube of copper and squeeze it between two rollers to make a wire. You pull it, and that pressure in pascals would then make the thing stretch. So here we're going up, we're adding a force, okay, and then we are taking that force off and you come back down here. This section is a plastic deformation section, and there's a new original length. Now something that's quite interesting is the energy. The total energy underneath the upwards graph, okay, all that is the energy in, okay, the stretching energy. Okay, how much energy you use to stretch. Then under the graph, let's change colour, sorry. Under the graph coming back, what is that? Well, that's energy out. Okay, so that's energy that could be used to, if it was a rubber band, to fire a bullet. Okay, you know, like a slingshot. So what about the difference? Okay, what happens to this energy here? Okay, well that goes away as heat. Okay, it's lost energy. You don't get it back. Or, not heat, sorry, it could also just be potential energy changes. Similar thing here, however, this one will go up. If it breaks, or it will come back down the same place. So brittle materials will be like glass. You know, you can bend glass elastically, you can push on it, but as soon as you reach the breaking point, there's not going to be much plastic deformation. It's going to end up just breaking. Polymeric materials, this is one where essentially the stress is not consistent with the strain. Okay, it changes, so there's changes in energy as it's being stretched. So you can see there's not consistent increase in energy. Okay, or energy required to stretch it, or force, it changes. Same thing here. You can have the energy to stretch. You can then have the energy you get back out. And that means heat is this energy there. How do we measure Young's modulus? Well, you need a device that measures a small change in length. Okay, we might look at this one in class, but this one here, as you attach a force down there, it's going to stretch this wire. Okay, it's going to get longer, and the little sticker will move along the ruler, giving you a new change in length. One of the most important ones here is this sort of diagram is quite interesting. Concrete stops compression, however it cannot hold tension. So whenever you build a girder like this out of something like concrete, you need to attach a steel in there to hold the tension.